Hey everyone, so I'm making this video to go over the second FRQ about polar curves on your notes. I just want to make sure you are able to get a good understanding of how to do the area with two different curves so that you're able to be more successful in your homework. So hopefully this helps you. So we have two polar curves, r equals 2 and r equals 3 plus 2 cosine theta. And we know the curves intersect at 2 pi over 3 and 4 pi over 3. So you can tell that r equals 2 is the circle because it has a constant radius. We just basically r is 2. That's representing a circle. And then the other curve, the bigger one, is 3 plus 2 cosine theta, which it's actually called a cardioid. And you can kind of remember that because it kind of looks like a heart. And heart, cardio, that's kind of how I can remember it. So they tell us that the curves intersect when the angle is 2 pi over 3 and 4 pi over 3. So you want to think about your unit circle and your angles to figure out which is which. 2 pi over 3 is going to be this intersection right here, right? If I draw my angle, this is the angle 2 pi over 3. So here theta is 2 pi over 3. And then 4 pi over 3 is if you keep rotating around to this intersection point. That's where theta is 4 pi over 3. So that's the information we've been given. Now, part A just wants us to find the area of R, which they've already shaded in for us. So with polar, we have our area formula, which is 1/2 times the integral from some angle alpha to beta of r squared d theta. So we know what r is. Depending on which curve we're looking at, and we need to figure out how to do this area. So we want to think when we're doing a polar area, we want to think about how we're summing up a bunch of like sectors of a circle. So, and I also with area, I'm always going, or not with area, with like a unit circle or with angles, we're always going in the counterclockwise direction. So we are always finding the area of a sector of a circle, and basically that sector always starts at the origin and then goes out to whichever curve we're trying to find the area between. So like from the origin to the circle, and that's kind of like, these are the sectors we're summing up to do our area. So you can see how these sectors look, and then you'll notice that when you get to 2 pi over 3, it switches. So we're no longer going from the origin to r equals 2, the circle. Now we're going from the origin to the cardioid, the edge of the cardioid, and that's where our sectors come from here. So if it helps you, you can kind of draw those sectors just to see what's happening. So and obviously we keep going around like this to get our full area. So we're going to have two integral or two area expressions for this because we have sort of two different curves we're looking at, and each part is using a different curve. So if I start with the green area, I can actually find this area using what I know about the area of a circle, or you can also use an integral. So there's kind of two ways you could do the green area. So the first way you can do the green area is thinking about it as a circle. So this is actually, you can kind of tell it's 2/3 of a circle. You can also tell by thinking about how the angles 2 pi over 3 and 4 pi over 3 lie on the unit circle. That top part is 1/3, the red part is 1/3, the green part is 1/3. So this is actually 2/3 of the area of a circle. So you could do 2/3 pi r squared, and r is 2 as the area for the green part, or you can do it as an integral if you can't really tell like that it's 2/3 of a circle. You can still do an integral. You can do 1/2, and then we're going from 4 pi over 3 to 2 pi over 3, but it's kind of weird to go from 4 pi over 3 to 2 pi over 3 because 4 pi over 3 is bigger. So we're actually going to call 4 pi over 3 negative 2 pi over 3 because that makes more sense. And then to positive 2 pi over 3 of r squared, which is 2 d theta. So either of those expressions will give you the area of that green section. And then the red section, we have to add on, that's going from, that's 1/2 the integral from 2 pi over 3 to 4 pi over 3. Again, we're going counterclockwise, of r squared, so 3 plus 2 cosine theta, because that's the curve we're going to, squared d theta, okay? And then since this is a calculator problem, you would just type it into your calculator, and you will get, when you add those two things together, 10.370 as the area. So that's just an idea of how you want to think about area. When you have multiple curves, you want to always think about going counterclockwise, and always think about going from the origin to the edge of whichever curve you're looking at. Okay, so now let's do part B. Part B is asking, a particle is moving along r equals 3 plus 2 cosine theta, so that's the cardioid, and the position is x of t, y of t, theta is 0 and t 0. The particle moves along the curve, so that dr dt equals dr d theta. That's basically saying the rate of change of its radius is equal to the rate of change. The rate of change of its radius with respect to time is equal to the rate of change of its radius with respect to its angle. Find the value of dr dt at theta equals pi over 3 and interpret your answer in terms of the motion of the particle. So first things first, if I know dr dt equals dr d theta, I can actually really easily find dr d theta because I already know r is 3 plus cosine theta. So I can just take the derivative of that with respect to theta. So that would be the derivative of 3 is 0, and then the derivative of 2 cosine theta is negative 2 sine theta. And then that's supposed to also be equal to dr dt. So if I want to know dr dt at pi over 3, I can just plug in pi over 3 to negative 2 sine theta. Sine of pi over 3. And that gives me negative 1.732. And we want to think about what that means. Since dr dt is negative, so this is less than 0, that means the rate of change of its radius with respect to time is negative, so its radius is getting smaller. And if you think about that, since the radius is the distance from the origin to its path, basically this means the particle is moving closer to the origin, So the particle is moving closer to the origin since dr dt is less than 0. Oh, and because the radius is also positive at pi over 3. So that basically means we have a positive radius, but it's getting smaller. So I should write at pi over 3. Okay. So that's a good interpretation. And then C, it's actually really similar. It's now saying dy dt equals dy d theta. Find dy dt at theta equals pi over 3 and interpret. So again, I can find dy d theta because we should know y equals r sine theta. And so I can plug in r. So y equals 3 plus 2 cosine theta. Oh, my 2 didn't come out. Times sine of theta. And then I can find dy d theta. Technically, this is a calculator question, so you could like completely do the derivative in the calculator. I'll do this one part by hand. You're going to use product rule. And then you would plug in pi over 3, and that equals 0.5, which equals dy dt, since dy d theta equals dy dt. And then what does this mean? I'm going to have to squeeze this in. So this is greater than 0. And since dy dt is the change in the y distance, the vertical distance, then that would mean that the particle is so it's increasing, it's positive, so it's increasing its distance away from the x-axis. So the particle is moving away from the x-axis because dy dt is greater than 0 and y is greater than 0 at pi over 3. So hopefully this gave you like a better idea of how to deal with the area, and also just an example of an FRQ that uses all the polar coordinates with calculus. So let me know if you have any questions. Hopefully this helped.